Hey Chem folks, we're back again. This time we're going to talk about Lewis structures and multiple bonds. Remember that the reason that atoms are bonding in the first place is to get the noble gas configuration. That's the driving influence, and that determines and explains a lot of the behaviors that we see in chemical reactions. So we're going to take a look at how do we show the electronic structure through a Lewis structure of different molecules. So we're talking about molecular substances here. Remember our rules that we reviewed in a previous video. Let's say we'll start with nitrogen. We know that nitrogen, which is a gas in our Earth's atmosphere, is diatomic. So it's two nitrogen atoms bonded together. So remember, that's step one. We need to know how many atoms of each element are involved. Now there's just one element involved here, but there's two atoms of that element bonded together. The next thing we wanted to know is, what is the arrangement? Well, obviously, with two atoms in the molecule, they're side by side. So that's our arrangement. The next step is, how many valence electrons? So we have two nitrogen atoms, and each nitrogen atom brings 5 valence electrons to the picnic. So we have 5 plus 5 is 10 total valence electrons that are going to be distributed in this molecule. The next thing we want to do is, remember, these are our jelly beans that we're going to have to distribute to show how the electrons are arranged in this molecule. So we're going to move over here, take our arrangement, the two nitrogens, which we know are side by side, and we're going to start distributing. I'm going to start following my rules. I know there's a pair of electrons shared by each of these nitrogens that are providing this covalent bond. So that's 2 electrons down. That brings our jelly bean pile down to 8. So I've got 8 left. The next thing I want to do is make sure that each atom ends up with the noble gas configuration. So I'm going to take and distribute 6 electrons there. That leaves me with 2. That gives this nitrogen 2, 4, 6, 8. That gives it the noble gas configuration. I'm going to put the other 2 over here. That's all I've got. That uses up all of the jelly beans in the pile. So I'm down to 0 here. I've distributed all of the valence electrons that are involved in this molecule. But I look at it and I see something is off. This nitrogen has 2, 4, 6, 8. This nitrogen is only showing 2, 4 valence electrons. And I just know that that's not correct, because I'm convinced that nitrogen is going to do everything it can to get a noble gas configuration, which for nitrogen is going to be 8 valence electrons. So what this means is this unshared pair must be an additional shared pair in there. So now I have 2, 4, 6, 8 for this nitrogen, 2, 4, 6 for that nitrogen. So I'm still short, where I only have 6 valence electrons here. So that must mean that I need to bring that unshared pair down in here and make it a shared pair. So this is how we begin to understand multiple bonds, and that the atoms are going to distribute electrons so that they are sharing what they need to share, which essentially bonds them, because the nucleus of each atom is pulling on those shared electrons, and that is the glue that holds them together. But they are going to end up with the noble gas configuration. So now I see this nitrogen has 2, 4, 6, 8, and this nitrogen also has 2, 4, 6, 8. And they achieve that by sharing 3 pairs of electrons, or 6 total electrons. Effectively, we have a triple bond. I can simplify this to use a line to represent each pair of shared electrons. And then I'm going to keep these unshared pairs in the Lewis structure, because these are significant to the electronic structure of this molecule. It's important to know that we have these 2 unshared pairs of electrons in the molecule and 3 shared pairs of electrons in the molecule. So there you have it. That's how we could end up with a triple bond. We looked at one example where we saw 2 nitrogen atoms bonding together to form a triple covalent bond. Let's look at a compound now where we end up with a multiple bond, or 2. Remember, first we start with what is the substance that we're evaluating. And in this case, I've chosen carbon dioxide. I need to know the formula, so I know that there's 1 carbon and 2 oxygen atoms in this substance. Recall that the next thing that I need to know is how are these atoms arranged? Is it 1 carbon bonded to an oxygen, bonded to another oxygen? Or is the carbon the central atom? We don't know the answer to that without doing further exploration or having a deeper understanding, which is beyond the scope of this video. So we'll just tell you, carbon is the central atom. So I have an oxygen and a carbon and an oxygen. So this is my arrangement of those 3 atoms that are in this molecule. Recall that step 3 involves what is the total number of valence electrons in this molecule. Oxygen brings 6 each. Carbon, as we know, brings 4. So we have a total of 16 valence electrons. These are the jelly beans that we need to distribute through the molecule to make sure that each atom ends up with a noble gas configuration. You've got to remember the significance of the noble gas configuration. My arrangement over here, where I have carbon as the central atom, bonded to 2 oxygens. And let's remember our steps. These are the jelly beans. We're going to start by putting a pair in between because we know that we can assume that there's at least a pair of electrons shared between the carbon and each of the oxygens. That takes up 4. So now I'm down to 12 jelly beans left that I want to distribute. The next thing that I do is I look at the non-central atom, which would be the oxygens, and I say I'm going to give the oxygen the noble gas configuration because we know that ultimately that's going to be what oxygen is going to figure out, how to arrange electrons so that it ends up with a noble gas configuration, which would be 8. So that would be 2, 4, 6, 8. And that was 6 electrons. So now I'm down to 6 jelly beans, 6 valence electrons left. I'm going to do the same thing over here. 6 electrons for that one. So this oxygen has 2, 4, 6, 8. It's got the octet. It's got the noble gas configuration. So things look great so far. Now I need to look at the central atom. And we can see here that carbon is only ending up with 4. And carbon's not satisfied with that. Carbon's going to want to have 8. So that means I've got to consider one of these unshared pairs as being an additional shared pair there. 2, 4, 6, 8 for the oxygen, 2, 4, 6 for the carbon. I'm going to do the same thing here. So I've shifted those to recognize all of the atoms involved in this molecule are going to end up with the noble gas configuration. So we see that oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And the carbon effectively has 2, 4, 6, 8. So we've got 2 pairs of shared electrons here and 2 pairs of shared electrons here. So these are double covalent bonds. And we do still have some unshared pairs which are significant to the electronic structure of the carbon dioxide molecule. We can simplify this down to use lines to represent the pairs. We want to keep our unshared pairs there around the oxygen to show the Lewis structure. So here's the Lewis structure, And here's another example of a Lewis structure simplified to use lines rather than jelly beans or dots to show the valence electrons and the bonded pairs. So there you have it. Nitrogen was an example in the previous video of a triple bond, and here we see an example of a double bond. Important for you to give some consideration to symmetry as the electrons are arranging. That's going to be a natural circumstance for the electrons as they repel each other and are attracted to the nucleus where the positive protons are. So there's going to be some even distribution happening as much as possible. These 4 electrons are pulled on by the nucleus of this oxygen and the nucleus of this carbon. These 4 electrons are pulled on by the nucleus of that oxygen as well as the nucleus of this carbon. So that sets up some electronic dynamics there that are going to be important for us to consider later on. Have a great day.